Welcome to the lecture 3, that is Introduction to Newton-Euler and Recursive Newton-Euler Expression. So in this lecture I'll discuss recursive Newton-Euler formulation, and I'll use that to derive equation of motion of a one link arm using recursive Newton-Euler approach. So let us continue. So why do we need Newton-Euler formulation? Once we have already learned there are many other approaches like Lagrange-Euler approach, why we still need this one? So Lagrange-Euler dynamic equation of motion that contains the terms with multiple derivatives. As you have seen, it has dou L by dou theta dot and d by dt terms. Those terms are highly derivative terms, and Coriolis and centrifugal components as well, which make it computationally inefficient for any real-time robot control. In case of real-time robot control system, you need to compute the dynamic equation of motion in real time stamps, right? So you continuously feed the data what is required trajectory, and you continuously calculate the torque based on these equations. So that is the reason it takes quite lot of time and it is not computationally efficient. Okay, so a simplified robot arm dynamic model may be used by ignoring Coriolis and centrifugal effect, which is suitable for slow moving robot and animations, but definitely it is still not suitable for faster moving system. So however, the Coriolis and centrifugal effects are significant in the joint torques when the arms moves very fast. At high speed, the errors in the joint torque resulting from the ignoring Coriolis and centripetal forces cannot be corrected because of excessive requirement on the corrective joint and joint forces and torques. Okay, so Newton-Euler approach allows recursive formulation and programming to obtain the runtime variables in real times. So let us derive that Newton-Euler recursive formulation first. This is Newton-Euler equation that we will be using. So Mi, this is the piece of the link which I have shown here. So Mi is the mass of the link. Okay. Vci is the velocity of the center of mass of ith link. Fi minus 1i and Fi I plus 1 are the forces that are coming from the both the directions on this link, one from this side, other from the link which is on the other side of it. Okay, coupling forces applied to link I by the links I minus 1 and I plus 1 respectively. This is link I, so I minus 1 will be here, I plus 1 will be here. Okay, similarly Ni minus 1i and I plus 1 are the coupling moments applied to the link I by links I minus 1 and I plus 1. Okay. Centroidal inertia tensor. So I is the centroidal inertia tensor and omega is the angular velocity of the link. So using free body diagram of the individual link I, you see all the forces are marked here. So now I can write the resultant of all the incoming forces should now create acceleration. So sum of all the forces should be equal to 0. So Mi Vci dot is basically arise due to the forces. These are the forces which are acting on the link. This is the gravitational force, this is the force from one link and force from the other link which is next to it. Okay, so they all create the Vci dot. Okay, and similarly moment, resultant moment due to all the moments. So Ni minus 1 I is the moment coming from here, I plus 1 is moment coming from here, and moments are also created like Ri minus 1 I, that is this vector, plus this vector, effectively it is this vector. Okay, so that is the vector, so with negative sign. So whatever is the force that is here, this creates moment at this point. So this is the, all the moments are considered about mass center location, that is Ci, and similarly for Fi I plus 1, there is, this becomes the vector. These two are the vectors which is actually creating the moment over here. So this is here, and I omega dot, that is the angular acceleration alpha I. So that is equal to, that is the resultant of all the moment basically. This is what is created, and omega cross I omega is the gyroscopic torque. So that is all added together, and sum of all those should be equal to 0. Okay. The complete equation of motion of robot is obtained by evaluating both the equations for all the links. For all the links you have to calculate these two equations, you have to create these two equations. Okay. So joint velocity and acceleration are calculated using forward recursion. So you already know that. So once you have a robot, so if I am calculating the, if I am considering the joint and link velocities here, okay, so all the links prior to this has an effect on the ith link. Okay. So any link which is coming after this, they do not affect the link velocity and angular velocities of this link, ith link. So all the links which are before this actually affects the link I. Okay. So that is calculated in forward recursion. Joint torque and forces are evaluated in backward recursion. You again know that we have done also in statics. So all the links, if I am considering ith link, so all the links which are after this will have effect on the joint torque or the moments which are coming on this link. So this link is affected, forces and moments of this link is affected by the links which are after this, not the link before this. So that is the reason it is done in the backward recursion. Okay. So note, the joint torque tau I is not explicitly involved in Newton-Euler formulation. Okay. So independent joint torque is not involved in this formulation. Okay. So now what is I? I is the symmetric positive definite matrix 3 cross 3 inertia matrix of link I about mass center location Ci. It is given by this. So mass moment of inertia, these are principal moment of inertia, that is Ixx, Iyy, Izz. You already know this. Rho is the density of this link, dV is the elemental volume. So rho dV is actually dm, that is the elemental mass. You integrate over the volume and you get the moment of inertia. Okay. Similarly, product moment of inertia Ixy is equal to Iyx, and that is given by this Iyz, Izy, Izx, Ixz is given by this. These are product moment of inertia. Okay. So forward computations. So in step 1 we calculate all the angular velocity propagation. Okay. So angular velocity of ith link is given by this omega I. So if there are two links, so omega I would be equal to omega I minus 1, that is for the link which is before to this, plus theta I dot into the axis vector. Okay, this effectively this is the total velocity at omega I. So omega I is equal to omega I minus 1 into theta I dot into EI. Okay. So this is the term, this is actually the angular velocity imparted to the ith link due to the motion of the joint angle theta I. Okay. And theta omega I minus 1 is the angular velocity right up till I minus 1th link. Okay. And in case of prismatic joint, both the I minus 1 and ith link will have same angular velocity, because you don't have any theta I dot there, okay. That is not a revolute joint. So whatever is the angular velocity of the prior link will become the angular velocity of this link itself, okay. Expressing the ith link frame, the same can be expressed in ith link frame like this. So what is Qi transpose here? If you remember, this is your forward kinematic equation for one link, okay, from link ai minus 1 to ai. So this is the transformation matrix, you already remember. So the upper 3 cross 3 transformation matrix actually contained the transformation matrix for Qi, okay. So over here it is Qi minus 1, so that is here. So that is the 3 cross 3 matrix that actually represents the orientation of the frame I attached to the link I minus 1 with respect to the frame I plus 1 attached to the link I, okay. So this is it, and this actually transforms the omega I minus 1 to ith frame, okay. So this is the transformation, this is already there in the ith frame, so some of them will actually create this equation, okay. So how is it happening basically? Let's see, let's say if you have a link here, okay, if you have a link here, if you have a link here, okay. So if there is any vector which is represented in ith link, okay, in the ith frame, so this is the vector. So there is a matrix which takes you from here to here, Qi minus 1, that is for the I minus 1th link. So if there is a transformation, orientation transformation matrix from here to here, and V is represented in this frame, if you have to transform this V to this frame, the frame prior to this, then you have to multiply this to this. So Qi minus 1 into Vi will actually express Vi in this frame, okay. So that is a method to bring it here. So if you have to do inverse, that means omega I minus 1 you have to bring it to other frame, you have to multiply with inverse, and inverse of Qi minus 1 would be equal to transpose of this. So that actually creates this term, okay. And this is the angular velocity due to the rotation of the joints, so that is here. So theta I dot is involved here, and Ei is the axis vector Ei, okay. So this part is due to the joint motion, this part is due to the omega, that is the angular velocity of the link which was there, okay, which was in this frame. So this multiplied by transpose of Qi gives you this. So this is how it is working, okay. So now angular acceleration propagation, you don't need to do much, you just take derivative of this. So what you should be getting, if you take derivative, omega I dot is equal to omega I minus 1 dot plus theta I double dot Ei and plus theta I dot, what will be the Ei dot? It is equal to Ei cross omega I, okay. So that is written here, okay, Ei cross theta dot omega I, okay. So that is the second part. So same, you just take derivative of that and you obtain this. And for prismatic joint it is very simple, whatever is the angular acceleration of previous link becomes the angular acceleration of this link also, okay. So now expressing in ith frames, similar as we did it in the previous slide. So exactly the same, you have to multiply this with Qi minus 1 inverse, that is transpose, that those are here, and it makes the recursive relationship for computing the angular acceleration of link I in terms of link I minus 1. So if you know for the ith link, you know for the I minus 1th link also. This way you can. Now let us look at linear velocity propagation, how it works. So whatever is the velocity of previous link directly comes to the ith link also, and these are the distances. So, this was your link, this is mass center location, this is Ri, and you have Di which was here. Okay. So, whatever is I minus 1, because of Ri it creates a velocity component, and Di, that is because of its own rotation omega I, it has a velocity contribution. Okay. So, velocity contribution due to omega I minus 1 and due to omega I, both are summed together along with the velocity because of the previous link. Okay. C I minus 1. So, that comes here, sum of all those is actually visible here. In case of prismatic joint, so whatever is the previous velocity will come here also, and you have Ri plus Di, that is single thing, and that is only because of the prior omega I minus 1 that will create the velocity to Ci. Okay. And because of its own extension or retraction, that is the velocity of the prismatic joint into the direction vector Ei. So, that creates a contribution. This time you also have Bi, that is also expanding, right. So, the prismatic link, rate of change of that prismatic joint comes here. So, that is also creating the velocity components. Okay. So, expressing again in the ith frame, you have to consider the Qi matrix here, okay, 3 cross 3 matrix, and Di is Ai minus Ri, that you already know. So, Ai is the link vector, okay, Ai, and you have Ri and Di, Ri and Di vectors. So, sum of them creates this. So, Ai is Ai cosine theta I, Ai sine theta I in terms of joint angles. You can write this. If you know, if you remember the DH parameter, you can directly obtain this. So, Bi is the offset, Ai is the link length, and theta I is the joint angle. Okay. Ri is Rix, Riy, Ryz. So, this is well known in its own frame. Okay. So, this is the recursive relation for computing the linear velocity of link I in terms of link I minus 1. Okay. So, now acceleration propagation, this is very simple, you just have to take derivative of whatever was here. So, let us take it. So, C I double dot equal to C I minus 1 double dot plus omega I minus 1 dot cross Ri minus 1, that is trivial, plus omega I minus 1, and what will be Ri minus 1 dot? It will be omega I minus 1 cross Ri minus 1 plus, again there are two components. So, it will be omega I dot cross Di plus omega I cross Di dot will be again equal to omega I cross Di. Okay. So, this is how you can do it, and similar is for this one also, and that comes here directly. Okay. So, that is for prismatic and revolute joint both. So, using in case of prismatic joint, omega I is equal to omega I minus 1 and omega I dot is equal to omega I minus 1 dot. Okay. So, expressing in the ith link frame again in the same way, we can use Qi minus 1 transpose to do that. So, this is the recursive relation for computing the linear acceleration of link I in terms of link I minus 1. Okay. Okay. So, acceleration due to gravity from I minus 1th frame to ith frame. Okay. So, the same thing we did it in statics also. Initially you convert G to the last link frame and then you recursively go back, or you already know the G in the first frame, you can move forward and keep calculating the G. But here it is shown as Gi minus 1 transformed to Gi using Qi minus 1. Okay. Now the backward computation. The force and moment required to be exerted at and about the center of mass of link I are this. Force is directly Mi Ci double dot, okay, and moment is because of two components. First one is moment of inertia into angular acceleration plus this is the gyroscopic component. So both of them will together create the moment component. So this is the force, this is the moment. Again the force and moment balance equation about center of mass of the link I are, this you remember, this is from statics also. So in case of statics, you see you don't had it was a balanced system was not moving, so the forces that are acting on the link from both the direction and due to its own weight, they are all balanced, okay. But in this case, that is also having a resultant force, okay. So that is shown here, so incoming force from both the direction and due to its own weight, so all the forces has a resultant force that is actually creating the motion. Similarly in case of moment, so these are the moments coming from both the directions. This is due to the both the sides, the joint forces, the forces which are there, that is creating moment at the center of mass location, okay, that is there. So that is also having a resulting moment. This can be rearranged in recursive form to do it like this. So the forces and moments can now be found recursively starting from the last link, okay. So you have to do it from the last link because it is force and moment. So all the links which are, so any, if it is this, so all the links which are after this link will have effect on this link moments and force, but not the links which are prior to this. They will not have any effect over here, okay. So at the end you have to calculate the actuator torque or the force depending on prismatic joint or the rotary joint. It can be obtained by projecting the moment or force onto the corresponding axis, okay. So that is done here and you obtain what is the joint force or the torque. So the tau is the last element of the vector Ni minus 1 I or Fi minus 1 I, okay. Okay, now let us see one example using recursive Newton-Euler approach. So this is just one link, okay, with the fixed frame one which is shown here, okay. So now the rotation matrix representing the orientation of frame 2, that is tip of this link with respect to the frame 1, that is the frame which is prior to the link 1 where link 1 is attached to frame 1. So that transformation is simply given as, you already remember, this is rotation of about z by an angle theta. So this becomes your, so you have x, you have y here, so z is perpendicular to this plane and rotation about that by an angle theta. So that gives you the rotation matrix for that. So that is cos minus sin, sin cos, 0 0 1 and 0 0 here. And similarly ai vector, in this case it is a1, so it is a cos theta, a sin theta and 0 0 because it is planar system, there is no component along z axis, cosine is along x, sin a is along y, this is the link length vector. So that is written here, okay. Assuming the links are homogeneous, the mass center location will be at the center, okay. So this is your r, this is your d, okay. So d will be equal to 1 by 2a, mid at the center it is there, cosine theta, sin a theta and 0. So that is here, half of this is d, but r is in this case it is from here, so it is along x, because you know this is your link x axis about which A is measured. So if you remember DH parameter and DH frames, so it is along x. So A by 2, 0 and 0. So assuming the link to be slender square beam, in that case moment of inertia will be equal to, about the center will be equal to, so about it is a slender link, so about its own axis, that is x axis, so it is 0, whereas about y and about z it is having components as ma square by 2 in both the direction. It is symmetrical, square, slender. Okay, so this is my moment of inertia. Okay, with this we will progress forward computation. Okay, angular and linear velocities and acceleration of the first link with respect to the fixed base are omega 1 is equal to this. It is along z axis, you know, omega, all the joint motions are about z axis. Similarly, rate of change of omega is this, and Ci dot is equal to Ci, you already have calculated here. So Ci is this. So rate of change of that point, so projection about x, projection about y, so it is a by 2 cos theta about x it has, and about y it was a by 2 sin theta. So when you take derivative, you get cosine is minus of a by 2 cosine theta, and sin a derivative would be cosine theta. Okay, and a by 2 will remain, and you have theta I dot. So it is r omega, omega is the joint rate. Okay, so V is equal to r omega, if you remember that, so that is here. Okay, so now when you calculate acceleration, you just take derivative of this. So first derivative, second part, and second derivative, first part. So it is exactly the same. I just took derivative of this, I could obtain this. Acceleration due to gravity, it is along x axis, which was downward as per the previous figure. So it is expressed like this. Okay, now doing the backward computation, that is from 2 to 1, we want to do the force and moment calculation. So as there is no external force, so this becomes equal to 0, and F1 will be equal to this. Okay, F1 will be equal to mass into acceleration, so it is this. So m is the mass of the link. Okay, m c double dot. Okay, so that is the term which is here. Similarly, the moment is equal to I theta double dot. Theta is in along this direction, I into alpha. So that is simply this one. Okay, when you express that in first link frame, if you remember the recursive backward formulation, okay, so you have to do this. If you see this, so in this equation you could see the forces as related with mg also along this ith link frame, so that makes it mg over here. Whole of this equation, the top row is considered here, okay, plus this mg force that comes when it is expressed in first frame, okay, F01 in 1, okay. Other terms remains as it is, so these terms as it is, okay. And for this, it is with respect to the first frame when it comes, it has, so moment of inertia effectively gets converted to, so if this is about this earlier, okay, now it will be about the tip of the center of rotation, okay. It is not about center of gravity. So moment of inertia get transformed and it comes about this, and you also see moment due to the mg into a sin theta, mg into a sin theta, half of that. Why? Because it is at the center, so that term is visible here. This is moment due to the center of gravity, okay, that is the gravitational force, and moment of inertia gets transformed to the axis over here, joint rotation axis, okay, and theta double dot. So that is there, okay. So when you take torque computation, here there is no force, so what you see just the last part of it. So if it is getting projected along the axis of rotation, only this term would be visible, and that gives me tau is equal to 1 by 3 because of this 1 by 3 ma square theta double dot plus this. So this is due to the inertia and this is due to the gravitational tau, okay. So that's all for this lecture. So in the next lecture we will cover dynamic equation of motion of two link manipulator using Newton-Euler approach. That's all. Thanks a lot.